More than 4.5 billion years ago, the solar system was formed from huge clumps of ice, dust, and rock left over from the creation of the universe. These clumps, called planetesimals, collided, growing in size as the larger planetesimals drew in smaller objects. Planet Earth was born from these molten collisions. The smaller objects not absorbed during the planet creation process were drawn to the outer edges of the solar system. There, just over 3 light-years away from the Sun, these comets and asteroids turned into an immense cloud called the Oort Cloud. The solar system, with its sun and planets and stars and Oort Cloud in tow, circles the Milky Way galaxy once every 225 million years. However, the 200 billion stars in the galaxy don't follow uniform circular orbits. They shift with each revolution. That sometimes brings the Sun and the Oort Cloud into close contact with other stars and interstellar clouds. These close encounters can disturb the Oort Cloud, spinning comets trailing long tails of cosmic debris out of their normal orbit and directly into the Earth's path.
These occur when a star comes very close to the Sun, perhaps within 3,000 astronomical units, where an astronomical unit is the Earth's distance from the Sun, or when we encounter a giant molecular cloud in the galaxy. These are very large clouds of interstellar gas where stars are forming, and these can really shake up the Oort Cloud and throw many, many comets in what we call a comet shower.
Organic materials from deep space that may have been the first living material to arrive on Earth.
So they have a very large organic carbon content, and we believe that this carbonaceous material is certainly a major contributor to organic material on the Earth. Right now, at present times, there are thousands of tons of this organic material falling on the Earth every year. And early in the history of the solar system, when life was forming, about 3.9 billion years ago on Earth, the flux of this material was probably even much higher. So this has been a natural source of organic material falling on our planet throughout its history. And it may have played a major role in the origin of life. We actually don't know.
Cratering comes about because there's debris in the solar system, and eventually we bump into it. The amount of debris decreases slowly with time, and so we expect the number of impacts to go down with time.
But then, to Mueller's great surprise, the glass beads began to indicate that 400 million years ago, the cratering rate increased rapidly. No one knows why.
That means the Earth also underwent this increase 400 million years ago to a level that was much higher than it had been for 2.5 billion years. Initial form of life developed in that 2.5 billion years to some very primitive life forms. But most of evolution took place during this period of 400 million years when the bombardment was 3 to 4 times higher than it had been previously. This certainly played a role in the evolution of life on Earth.
When a graph of the cratering rate on the Moon is superimposed on a graph showing the number of species on Earth, the increase of both happens simultaneously. This points Mueller to the hypothesis that diversification of new species on Earth was stimulated by cosmic impacts.
Microbes can easily survive a journey through space in the most extreme environments if encased in a meteor, asteroid, comet, or even an envelope of ammonia, methane, carbon, water, ice, or a thin coating of dust only half a micrometer thick. On Earth, all manner of creatures are able to live and thrive under almost every imaginable condition, from miles beneath the Earth, deep within oxygen-depleted iron cores, covered in salt, under extremely caustic alkaline conditions, in poisonous pools of boiling sulfur, and in acid lakes. Extremophiles can flourish even under the most extreme life-neutralizing conditions. Extremophiles such as Thermus aquaticus flourish in scorching, boiling hot springs where they live happily alongside algae. Hyperthermophiles prefer even harsher environments such as the midst of undersea volcanoes. Bacillus infernus thrives even miles beneath the Earth where the sun never shines and where the weight and pressure is 300 times that of the surface and where scorching temperatures can incinerate most living things. The bacterium Deinococcus radiodurans is almost indestructible. Radiodurans can easily survive nuclear explosions and atomic radiation 3,000 times stronger than that which would instantly kill a human. Bacteria such as M. frigidum prefer ice-cold environments, and a variety of microbes have been discovered living in the frozen ice of Antarctica, including at Lake Vostok. Richard Hoover of NASA discovered fungi, algae, cyanobacteria, nanobacteria, spores, diatom, and protozoa in deep ancient ice cores over 4,000 years old, drilled from Lake Vostok near the South Pole. These creatures were also found in association with ancient cosmic dust particles which had fallen from space. Under sudden extreme changes of temperature, extremophiles instantly create heat shock proteins, cold shock proteins, or endospores which wrap around and protect them, enabling them to survive the infernos of hell or in freezing temperatures well below zero. Even under life-neutralizing conditions that threaten instant death, these creatures can instantly form spores or become dormant and exist in a state of suspended animation for hundreds of millions of years, only to reawaken and begin multiplying when they arrive in a life-sustaining environment. In 1995, 40-million-year-old bacteria, Bacillus ferricus, was found in the stomach of a bee encased in amber. These microbes had become dormant, forming spores, but were reanimated in a laboratory. In 1972, a Russian scientist, Professor Shudinov, brought bacteria back to life which had been embedded for over 250 million years in crystals of potassium in the Ural Mountains of Russia. When they awoke from their long slumber, they began to reproduce. In the year 2000, Professor Vreeland reported a similar discovery. He brought microbes back to life that had been embedded in salt crystals buried 569 meters beneath the Earth and dating back 250 million years. These bacteria, B. permians, survived by creating spores. Some of these bacteria began multiplying once they were brought back to life.
This theory is called Panspermia.
Panspermia is the theory that life formed in one place and then got spread around to other places. In outer space, in the medium between stars, we see molecules that are the building blocks of life. So it's easy to get the building blocks of life to another planet. For example, if life formed on Mars, it could have come here to Earth, contaminated Earth, and then started life here.
Roughly 3.6 billion years ago, Mars was warm and wet, much like the conditions on Earth today. Biologists believe that because Mars cooled more quickly than other planets, life may have developed there first.
Mars is a better candidate for life during the early part of the solar system. Mars rocks are coming here all the time, and these have been knocked off Mars by asteroid and comet impacts. And we know that they could convey any Martian microorganisms to Earth.
In August 1996, a team of scientists made a stunning announcement. A Martian meteorite found in Antarctica contained evidence of fossilized life. The 4-pound rock, designated ALH 84001, showed the presence of carbonate globules excreted by microbes when they were alive on Mars 3.6 billion years ago. Earth was no longer alone. Life had existed elsewhere in the universe.
So this cross-contamination between Mars and Earth, which 20 years ago was regarded as a rather wild conjecture, is now pretty much accepted by the astrobiology community.
Astrobiologists studying the origin and evolution of life in the universe embraced the possibility that life on Earth began in outer space.
The ultimate implication of some exobiological theories is actually that we ourselves are extraterrestrials, that life on Earth arose because organic material was brought here from elsewhere.
British geneticist Francis Crick is best known for his collaboration with James Watson. Together, they unraveled the structure of human DNA in 1953. Less than 10 years later, they were awarded the Nobel Prize for their groundbreaking work in genetics. In the 1960s, Crick became a proponent of panspermia theory and took it to a whole new level with an idea he called directed panspermia.
Francis Crick hypothesized that somewhere perhaps on the other side of the galaxy there had been a civilization of advanced intelligent beings. And they had found that their planet was going to be destroyed. Perhaps a supernova was going to go off in their vicinity, and their planet would be sterilized of life. And he asked himself, what would an intelligent civilization do in that situation? Well, first of all, they'd try to figure out if they could get out of there, if they could actually preserve their lives and the lives of their descendants, perhaps crowd into spaceships and fly across interstellar space until they found a suitable planet to colonize.
But could it actually be true? Could we really be the descendants of an alien race that traveled here from another world?